We are presenting the paper Generalizing and Decoupling Neural Collapse via Hyperspherical Uniformity Gap. Neural collapse describes a phenomenon of feature geometry when a neural network is overtrained. In neural collapse, the feature learned by such a neural network forms a simplex equiangular tight frame. Here is a simple visualization of neural collapse. However, the original neural collapse has an obvious pitfall. Simplex ETF does not exist when the number of classes is larger than the dimension of feature, but such a scenario is ubiquitous in practice. To address this, we propose a generalized neural collapse hypothesis where we replace the property of convergence to simplex ETF to the convergence of hyperspherical uniformity. We first show that generalized neural collapse provably covers the case of neural collapse in Theorem 1. Namely, simplex ETF is a global optimum for GNC. Why is generalized neural collapse so interesting? First, GNC fully covers the case of NC, while being able to generalize to the case of D smaller than C. Second, similar to NC that connects frame theory to deep learning, GNC connects potential theory to deep learning. Third, we use a variational characterization of hyperspherical uniformity, which is easily optimizable and gives us natural learning objective, unlike NC. Last, we can prove that the widely used cross-entropy loss also converges to GNC. We also empirically show that GNC indeed holds in practice, verifying the effectiveness of the GNC hypothesis. We show experiments on NIST and SAFAR 100. The experiments on ImageNet is given in the appendix of our paper. Additionally, we also have some theoretical results in the case of D smaller than C. Theorem 2 shows that cross-polytope is also an optimum for GNC. Theorem 3 connects hyperspherical uniformity with minimizing hyperspherical energy. Then we decouple the GNC hypothesis for designing a new loss function. With the characterization of uniformity, we identify a quantity called hyperspherical uniformity gap, HUG, that serves as an alternative and more flexible loss function than cross-entropy. The general version and proxy-based version of HUG is given in the slides. It provably minimizes mutual information between latents and targets. We consider three variational characterizations of hyperspherical uniformity in this paper. This results in three simple variants of HUG, as shown in the slides. Now we empirically show the loss surface for both cross-entropy and HUG. We can see that HUG exhibits more smooth loss landscape. As a decoupled loss function, HUG is very flexible, in the sense that it can use randomly initialized proxies. The learned 2D feature visualization is also shown here. We can see that HUG shows more discriminative features and more aligned proxies. HUG also shows strong out-of-distribution generalizability and adversarial robustness.